Welcome back. Today I'm going to talk about slope fields. Now, the textbook really doesn't talk about this because it either assumes you know it or it's easy or something, but this is what's going to help you visualize and understand how differential equations actually works. So let me give you an example here. See, let's start off with something simple. So this is a very simple idea. But if I have a differential equations, y is equal to, or the derivative of y with respect to x is equal to x. Now, of course, everybody knows that the answer to this is going to be y is equal to x squared plus a constant. But let's pretend we don't know that for a second. If I make a graph right here, every single point I'm going to use, now it's first, before I get too excited here, I'm going to call this my function f of x comma y. Now this one doesn't actually have a y value, and that's okay, right? Remember from Calc 3 you can have one just in one variable. And this is also my slope. So now, if I go, say, 1, 1, at this point 1, 1, the slope is going to be 1, 1, which is just 1. So the slope is going to have slope 1. And at the point 1, 2, 1, 2, so if I just put that point in there, 1, 2, that's also going to be 1. So you can actually see that the slope of each one is going to be 1. And I just put a little mark to indicate what the slope actually is. Now if I go to 2, m is equal to, or let's even do one even easier, how about f of 0, 1? Well, in that case, I'm going to put a dot down, and the slope is 0, because it's just whatever the x value is. So the slope is 0 for each one of these little guys. So m of f of 0, 2 is 0. Now let's go back 1. The slope at negative 1, 1 is just negative 1. So I'll make this a little bit exaggerative and move it a little bit more to the left so we can see it. So at negative 1, 1, the slope is negative. And the slope of negative 1, 2 is also negative 1. So you can see that there's a pattern to this, right? And so for example at 2, the slope is going to be double the other one, so forth and so on. So let me actually show you a computer-generated model of this from Mathematica. So here's what we see. Okay, this is going to be, our slope field is dy over dx is equal to x. Now what the lines mean is that if I were to try to draw, like if I were to pick some initial point, let's say here, if I just pick that as my initial point, then I'd want to follow it. I'd want to follow it so that all these things are tangential to the curve. And you can see that if I pick any point, that I'm going to get y is equal to x squared plus c, and that c is going to change depending on what point we pick. But the idea here is that dy over dx, this is our function, that's our slope. And that's going to be very important when we talk about Euler's method, our first numerical technique. Because you can almost see what the idea is, right? We're going to pick any point and then just follow that point along. So let's take a look at a better example. All right, this is one of my favorite examples. We have dy over dx is equal to e to the negative x squared. And for those of you in statistics should recognize that. if we try to integrate both sides, you're going to get the integral of e to the negative x squared dx. And if you punch it in your calculator, which of course really isn't a proof, or you try to punch this in online, you're going to see it's going to give you some weird answers. But there is an actual proof that shows that there is no elementary function that exists that satisfies as being an antiderivative of this thing. Which means we can't really figure out what the function looks like or behaves like. But the slope field is very easy. So for example, if I let f of xy, which is my slope, just equal e to the negative x squared, that's just slope, you can see it's easy to compute. If I put in 0, 1, that's just going to be e to the 0, which is 1. So at the point 0, 1, I just have that little bitty dot. And even though I can't solve this thing exactly, I can figure out how it behaves and what the long-term behavior is. So for example, if I pick a point here around negative 1, 1, and I put a dot down, I can follow it and see it's going to behave like that. Or if I pick another point over here, for example, if I pick something, it'll probably behave some manner like that. And you can see that we have this sort of what's called asymptotic behavior. And we can see how this thing behaves and what the function shapes are and whether or not it's increasing or decreasing. Now, this is what else is cool about differential equations, is that we are given that the slope, which is dy over dx, whoops, didn't write that right, dy over dx, which is e to the negative x squared, we know that's going to be positive for all x and y in the reals. So that means that no matter what I draw, it should be always increasing. And just to be clear, these little points here, like this point here, this negative 1, 1, or this one here, this looks like about negative 2, about negative 2.4, negative 2.4. Those are the initial conditions. And so you can actually see what happens if we have that specific initial condition. We can see what the graph looks like and how it behaves. All right, so this last slope field is pretty nice because it actually has, this is the first one that we have that has more than one variable as part of its definition. So this is going to be x squared minus y. So for example, here we can see that if I let this be my slope function, so my slope is f of x comma y, then if I put in the point m is equal to, say, 1 comma 1, that's going to be 1 minus 1, which is 0. If I put in the slope at 0 comma 1, then I'm going to get 0 minus 1, which is negative 1. And if I put in f of, say, 2 comma 1, or 2 comma 2, let's do 2 comma 2, that's going to be 2 squared minus 2, which is equal to 2. And these are very easy points to pick. So let me show you the first one. At the point 1, 1, so if I look at the point 1 and go up to 1 over here, you can see that it's roughly about, the slope is about 1 at that point. If I go to 0 comma 1, which is about here, you can see the slope is going down. It's negative 1. And if I put in the point 2 comma 2, which if I follow that through goes from 2 all the way up to 2, so it's this one at the very tip, you'll see that that one has slope that's twice as big as, say, this one. And this one, of course, is slope negative 1. So it's right about there. So you can basically just pick points randomly to fill out the actual entire graph. Like that's what this does. The computer actually will generate each little slope and figure out what the slope is supposed to be. I'll give you the Mathematica code for this so you can actually type it in and play with it yourself and come up with some pretty cool examples. Now another thing that's neat about this is, check this out. If I pick this as my point, notice that they all kind of asymptotically go together. They all asymptotically kind of, I don't want to say converge, but they all kind of go to the same limiting factor. Even if I pick this green point right here, you're going to see that they all travel to almost this asymptote, this vertical asymptote. Now this isn't a difference equations class, so I don't really want to get too stuck onto the details about how all this works. But what I do want to mention is that we can start to actually solve these things numerically. And this is sort of the visualization that I want you to have as you try to solve these things, like with Euler's method and the improved Euler's method and the Runge-Kutta method.